Alright, in this video here we're going to be talking about the inverse sine function. Now, before you even watch this video, there's a couple things you should be aware of. First off, inverse functions. I did a bunch of videos about inverse functions and some of the properties of inverse functions and what an inverse function means. So if you haven't seen those videos or you don't remember what an inverse function is, you might want to check those out before you watch this one. Also, the videos that I've done about the trigonometric functions, the sine functions, the graph of the sine function, and that kind of stuff. All those things are important to understand, or at least have some idea about those things before we start talking about the inverse sine function. Right? But if you remember what inverse functions are, if you remember the information we know about the sine function, then we're ready to talk about the inverse sine function. All right, so here's a graph of the sine function, right? Y equals sine of x, which I labeled that down here, kind of in a weird spot. But that's the graph of the sine function. And again, I did a video about the graph of the sine function, so if you don't know, you're not familiar with this, you don't know where that came from, check out the video I did just on the graph of the sine function. But that's the graph of the sine function, right? So we want to find the inverse of that sine function, right? The inverse sine function. So the thing about inverse functions that you need to remember, one, it's a function, right? What the definition of a function is that for every x value, there's only one single y value, right? For every input, there's only one output. And the test we use on the graph to see if something's a function is the vertical line test, right? We can see that the sine function passes the vertical line test because anywhere I draw a vertical line, which represents one single x value, it only hits the graph one time, which means that one x value only has one single y value, so it is a function. All right, but for a function to have an inverse, recall that it has to be what we call a one-to-one function. All right, so what a one-to-one function is, right? A function is for each x value, there's only one y value. A one-to-one function says that for each y value, there's only one x value. All right, so it's kind of going in both directions for a one-to-one function. Right, and the test we use for a one-to-one function is the horizontal line test. And we can see for the sine function here, it's going to fail the horizontal line test. Right, if I draw a horizontal line across this graph, it's going to intersect the graph. If I draw that horizontal line between -1 and +1, which is the range of the sine function, anywhere in there I draw a horizontal line, it's going to intersect that graph an infinite number of times. Because remember, this is not the whole graph here. It continues in both directions. Those waves keep going in both directions forever. Right, so the sine function does not pass the horizontal line test, which means it's not a one-to-one function. Right, for one single y value, for y equals 1, well, there's this point up here at pi over 2, there's this point over here at -3 pi over 2, and there's another one down here and another one after that, and there's more that way. Right, so for each y value, we end up with more than one x value. It's not one-to-one. All right, which means since it's not a one-to-one function, well, we can't do an inverse of the sine function. But we have to be able to do an inverse of the sine function because to solve equations that involve the sine function, if I know the number y and I'm trying to solve for x, well, in order to do that, I need to do the inverse of the sine function, just like for anything else. Right? If I'm trying to solve an equation, x plus 3 equals whatever, well, the inverse of plus 3 is -3, right? So I subtract the 3 to the other side. Well, to solve for the x in a sine function or a sine equation, I need to do the inverse sine. So there has to be some way that we can work it out to have an inverse sine function. And what we do in order to make that happen, in order to force the sine function, the graph of the sine function here to be one-to-one, I limit the domain of the sine function. Right? So what I want to do here is I want to kind of erase a whole bunch of the graph of the sine function and just leave one little part of it that is a one-to-one function. And that part that I leave, I want it to cover the entire range of the sine function. Right? So remember, the range goes from -1 up to +1. So I'm going to start down here where the graph is at -1, right, which is at the x value of -pi over 2. Erase everything to the left of that. Right? So starting here at -1 and then going up to 1 when x is at pi over 2, and I'm going to erase everything to the right of that. Right? This is the graph of y equals sine x when x is between -pi over 2 and +pi over 2. And that graph is now one-to-one. Right? Because now if I draw a horizontal line anywhere across this graph, it's only going to hit it one single time. Right? So it covers the entire range of the sine function, every point from -1 to +1, right? It hits them all, but it only hits each one of those y values one single time. Right? So if we restrict the domain of the sine function to just be between -pi over 2 and +pi over 2, then we can create an inverse sine function. All right, so for all of the trig functions, in order to have an inverse function, we do have to limit the domain, right? Because all of the graphs of the trig functions are periodic, which means they repeat the same values over and over again, which means none of them are going to be one-to-one, right? And we'll see this again. I'm going to do other videos about like the inverse cosine, the inverse tangent functions. It's going to be the same story or a similar story with those, right? We have to limit the domain so that we can actually have a one-to-one function and then create an inverse. Right, so the sine function, when x is in between negative pi over 2 and positive pi over 2, is 1-to-1, and so we can have an inverse sine function, which is graphed down here. Now, one note before we move on. This is not the only way you can limit the domain of the sine function in order to make it 1-to-1. Like, I could have picked the points from pi over 2 down to 3 pi over 2 and had everything from 1 down to -1. That also would have made it a 1-to-1 function, but by convention, mathematicians decided, well, we're going to limit the domain of the sine function to make an inverse sine. These are the values we're going to use between negative pi over 2 and positive pi over 2. That part right in the middle, around the origin, that's what mathematicians decided to use for the inverse sine function. So that's what we use, right? But there are plenty of other ways you could limit the sine function to make it 1-to-1. Basically, any part you leave up here from the original graph that goes from -1 to +1 or from +1 down to -1. Is going to be 1-to-1, right? But this is the one that mathematicians decided would make the most sense to use because it's right in the middle and it's centered around the origin. So that this is the one we use for inverse sine. All right, so if we limit our domain of the sine function between negative pi over 2 and positive pi over 2, the inverse sine function looks like this. Now remember, the notation for an inverse function is that -1 exponent. Remember, that doesn't mean sine to the -1 power. It doesn't mean like the reciprocal and flipping over the sine function. Right, the -1 exponent refers to the inverse function, right? And that's something I talked about when I did those videos on inverse functions. That's the notation we use for the inverse of a function, right? So sine with a -1 exponent means the inverse sine function, right? And remember, one of the properties of inverse functions is they switch the inputs and the outputs, the x's and the y's, right? So for my sine function, I'm going from x is negative pi over 2 to x is positive pi over 2. For the inverse function, those become the y values. I go from y is negative pi over 2 up to y equals positive pi over 2, right? For the inverse, or for the original sine function, my y's went between -1 and +1. For the inverse, those become the x values. I go from x -1 to x equals +1. And basically, if I take this graph up here and I reflect it around the line y equals x, remember, inverse functions, the graphs of them are reflections around the line y equals x. So if I take this graph and like flip it that way, like diagonally, I get the graph of the inverse sine function. All right, so this is the graph of the inverse sine function. Notice that the dots here, right? It starts from x equals -1, it ends at x equals +1. That's the entire graph, right? The inverse sine function does not exist outside of the x values -1 to +1. It does not exist outside of the y values negative pi over 2 to positive pi over 2. It's not like the original sine function where the wave keeps going forever. This one just goes from here to here, and that's the whole picture, right? And the reason we have to do that, remember, if I did the original sine function and then I switched the x's and y's, this would be like an up and down wave. It would be going like this, up and down. But that would not be a function, right? Because that would not pass the vertical line test. If I repeat these waves, keep going up and down, it's going to fail that vertical line test, which means that the inverse would not be a function. Right? In order for the inverse function to actually be a function, it has to pass the vertical line test, which is why that original one had to be 1-to-1. Right? If this one passes the horizontal line test, this one's going to pass the vertical line test, and it's going to actually be a function. Right? So that's the reason we need this to be 1-to-1. The reason we need this to limit the domain is so that when we do the inverse, it's actually a function. Right? Hopefully that makes sense to you. Just picture it. If you continue the wave up and down, and the vertical line test is going to hit that wave an infinite number of times. It's not a function, right? So we just take it from this point to that point. That's the entire graph of the inverse sine function. That's the entire existence of it right there, right? It doesn't go beyond that. All right, so the definition of the inverse sine function, right? The inverse sine function, sine inverse, right? That sine with a -1. Remember, we don't read that sine -1. We read it, in words as sine inverse, right? So sine inverse with domain -1 to 1, right? Again, the x values go between -1 and +1, including those endpoints, right? We have the brackets there because it does hit the points at -1 and +1, right? Because this one hits the y values at -1 and +1. And the range from negative pi over 2 to positive pi over 2. Also, brackets, those 2 points are included. So the y values go from negative pi over 2 to positive pi over 2. And then the definition of it, sine inverse of x equals y, means the same thing as sine of y equals x. Remember, for inverse functions, the inputs and the outputs, the x's and y's, get switched around, right? So when I'm trying to evaluate an inverse sine function, and I'll do an example or two of this in a minute, when I'm trying to evaluate the inverse sine function, basically they're giving me the answer to it, and I'm trying to find what if I think about it in terms of the sine function, they're giving me the x. I have to figure out, well, the sine of what number is going to give me that x, right? And the number I choose has to be between negative pi over 2 and positive pi over 2. Right, I'll put up an example of this in a second. Right, now one other thing before we get to an example, the inverse sine function is also called arcsin. Right, and when we get a little bit later in trigonometry and I do some more videos about it, I'll explain at some point why they call that arcsin. There's a reason for it, why the inverse sine function also has that name, arcsin. It has to do with like measuring the length of the arc of a circle, which is a section of the circumference of the circle. We're not quite ready for that yet based on the stuff I've talked about so far. But when we get there, I'll explain in more detail why we call that arcsin. But there are 2 different notations for the inverse sine function. You have the sine inverse with a -1 or the arcsin. They both mean the same thing. Right? So some problems you might see with this notation with a -1 exponent, some problems you might see with the arcsin notation, just know that they mean the same thing. Right? They're asking you to do the inverse of the sine function no matter which notation you're looking at. All right, so that's the definition of the inverse sine function. Let me erase some of the stuff at the top, and I'll put up an example or two real quick to go through where we evaluate the inverse sine function, just so you get a feel for what it's like. All right, so I'll do up here one example real quick of just evaluating the inverse sine function, and then I'm going to do another video where I go through quite a few more examples where we just evaluate the inverse sine function. All right, so I'm asked to find sine inverse of square root of 3 over 2. All right, so sine inverse of square root of 3 over 2. So basically what they're giving me when I'm doing the inverse sine function, they're giving me the output value of the sine function, right? Remember, inverses switch inputs and outputs. So what I'm looking for, really, when they ask me sine inverse of root 3 over 2 is sine of what gives me root 3 over 2. Right, the sine of what number is going to give me root 3 over 2, right? So they're giving me, whatever number's in the parentheses here is the output of my sine function, and I have to figure out what that input is going to be, right? And to do that, we use the unit circle. All right, so now for the unit circle, though, remember, for my sine inverse functions, the range is between negative pi over 2 and positive pi over 2. So my answer has to come just from negative pi over 2 to pi over 2, or just from the right half of the unit circle. Right? Remember, we had to limit the domain of the sine function to create the inverse. So when we're evaluating the inverse sine function, we're only using part of the unit circle, right? So just like we limited the domain of the graph, well, we're limiting the part of the unit circle that we have to use to make this work. Right? So what I'm looking for now is just on the right half of the unit circle, because that's where my t values are between negative pi over 2 down here to positive pi over 2 up here, right? I want to find where sine is equal to root 3 over 2. Well, what's the definition of the sine function in terms of the unit circle? Well, the sine function gives me the y-coordinate of the terminal point on the unit circle. Right? So for the sine inverse of this number, I'm looking for right half of the unit circle. Where does my y-coordinate equal root 3 over 2? Right? And notice, on the right half of the unit circle, there's only one place where the y-coordinate equals root 3 over 2, and it's way up there, the one I can barely reach. Right, that's that point up here. Right down here we have negative y values, 0, and then positive y values up to 1. Right, it covers all the y values, all the values that the sine function can take on, just on that right half of the unit circle. Right, so we get that point up there, and then what's the value for that point? Well, what's the pi number for that point? And if you remember the trig hand, if I put down this one, it's 1/2 root 3 over 2, and this finger represents the pi over 3. All right, so sine inverse of root 3 over 2 equals pi over 3, because sine of pi over 3 equals root 3 over 2. All right, so that's my evaluating that sine function, or that sine inverse function. Right, I'm given the output, and I have to find the input value for the sine function that gives me that output, that gives me this y-coordinate for my terminal point on the unit circle. All right, I hope that one made sense, just to give you an idea of what evaluating the inverse sine function looks like. I'm going to do another video where I go through a whole bunch more examples. I'm just going to put up a big unit circle and just do a bunch of these. So make sure you check out that video so you can see some other examples evaluating the inverse sine function so you really understand how it works.